we are currently in the 4th day. On the 3rd day, your Kamalika ma'am has told you regarding the supervised and unsupervised learning. To just carry forward that particular topic, one of the basic algorithms of the supervised learning is the support vector machine. Today, we'll be starting this particular lecture with the brief introduction about the theoretical parts, theoretical concepts about the SVM, that is a support vector machine. Then we'll be talking about how to implement this SVM for the sign language recognition problem. So first, we'll be talking about the theories of the support vector machine or the SVM. So SVM is a part of linear discriminant function. So first, we are going to have the overall idea what is linear discriminant function. Then we'll be moving to SVM. Then the application of SVM with respect to one published paper that will be discussed. So I'll be starting the screen sharing. See, for this particular thing, you can follow this particular book from where this lecture physically has been taken. So this is the reference material for this particular lecture, that is the linear discriminant function. Why is linear, why it's discriminant, and why it is a function? So basically it is a type of function by which discrimination is done in the linear concept. That is, if you have two class of data, I hope you already know what is class and what is clustering. As class, basically, that is the classification is from the supervised learning domain. Clustering is from the unsupervised learning domain. So in the classification problem, that is in the class, if suppose you have two class of data, you need to discriminate, that is you need to divide those class of data. If you can divide those class of data in the using a linear method, so that is the linear discriminant function that we are going to talk to. So there are two different approaches are there. One is generative, another is discriminant. That is our topic. So that is generative. This particular approach basically takes into account the probability distribution of data. But the discriminant native approach that is done without assuming the probability distribution in the data. So what is discriminant? That we need to talk. So here we are talking about the linear discriminant. That is the hyperplane that you are going to draw, that will be linear of nature. So for the preliminary concept, we are going to talk about the linear discriminant for two categories of data. Suppose you have two class of data. So for that, the linear discriminant can be represented by this particular function that is given over here. So that is the gx, that is the equation for the function. That is gx will be this w. What is the w? W is the weight vector. That is would be transposed into x, and x is the input values plus w0, that is the bias or the threshold weight. Now this particular thing that you can represent it in this summarization format, where I is equal to 1 to d, that is there will be d number of data for d number of cases we are considering this particular equation. So that you can represent by this particular equation. So now we need to decide the w1 if gx greater than 0 and w2 if gx less than 0. And if gx is equal to 0, then x lies on the decision boundary and can be assigned to either of the classes. So that is, you need to design a decision boundary where gx value will be equal to 0. So that is, this particular equation value will be equal to 0. This value will be greater than 0, then it will be basically class 1. If that value is less than 0, then that will be class 2. That is the linear discriminant function. So here you can easily understand the linear discriminant function. The decision boundary. So this is the decision boundary. And here you have two class of data. One is the red class of data, that is the region R2. One is the black class data, that is the region R1. These two classes of data can be plotted in the X1 and X2 region. So that is, this is in the two-dimensional. We have plotted two class of data, and for each class you have two data. That is, in the class 1 you have two data points, in the class 2 you have two data points again. And we need to discriminate these two class of data by a decision boundary. And the equation for the decision boundary is gx equal to 0. And this is our current hyperplane. The orientation of the hyperplane, that will be determined by the W. This is the W, right? And the location, that will be decided by the W0. And this was the equation that is taken from this particular slide, that is the previous slide. And W is the normal to the hyperplane, that is this normal distance, that is the hyperplane is this is the decision boundary, that is the hyperplane, and the normal, that is the W. And if W0 equal to 0, it passes through the origin. So if this particular, in this particular equation, this particular value is now 0, so that means decision boundary will now passes through the origin. So by use how you can estimate the decision boundary, that is how we can decide that what will be your decision boundary. How you can do this? That is, use learning algorithms to estimate W and W0 from the training data XP. So in the last class, we have already discussed about three types of data set: training, validation, and testing. So from the testing data, suppose for one particular XK of the data, we need to estimate W and W0. And let us suppose that is ZK will be 1, that is plus 1, that is the true class level if XK belongs to W1, that is in the class 1, and it will be minus 1 if XK belongs to W2, that is the class 2. And these are the true class levels. So what does that mean? So in the training data set, your data will be assigned with their corresponding class level. That is, they will be labeled with their corresponding class. Why? As it's a supervised learning algorithm. And with the supervised learning algorithm, data are mapped with their corresponding class levels. So that is, for the supervised learning, these class levels are present. So this is the true class level, that is the actual class level. After doing the learning algorithm, suppose we are doing the SVM, suppose vector machine algorithm. So then after that, you can predict some class levels. That will be the predicted class levels. These are the actual class level, that is the true class level. Apart from that, you can have another, is the predicted class level. And what is the error? If here you have plus 1, but you have getting as minus 1, so that is the error. That is, misclassification is done. If the true class level is plus 1 and the predicted class level is plus 1, so that means no error. That is proper classification is done. So this is the predicted class level that already discussed. So that is the Z bar, right? So that is if it is plus 1 and it's again plus 1, so no error is there. And when it will be plus 1 if g of xk greater than 0, and when it will be minus 1 if g of xk less than 0. So if you are not seeing that this is not a familiar thing, just check the previous slides. This has already been explained over here, that this is the decision that we have to take. So it will be plus 1 for here and it will be minus 1 for this class 2. That has been represented by the equation format over here. That's an error function. That is the training error or empirical risk. That will be 1 by n, k is equal to 1 to n. That is, suppose there are n number of data points. And this j, that will be a function of w and w0. Why? We need to estimate these two. So these two variables will be over here. So it is basically j is the function of these two. So just check this particular equation over here. X is a fixed, right? X are the data points. So those are the fixed things. In this particular equation, what are the variables? W and W0. So that is J will be in this format is equal to 1 by n, K is equal to 1 to n, and then ZK minus ZK bar square. So that is a ZK over here is that, and this is a ZK bar. So if there is a mismatch in the classification process, so this particular value will be not 0. And is it squared? Why square? So it suppose it's -1. The true class level is -1, and you are getting predicted class levels as +1. So what will be the result over here? -1 minus of +1. So it will be minus of 2. Minus of 2 square, that is the 4. So that is the minus thing. That is minus of 2. That is the minus thing that we need to neglect. For that reason, we have taken the square thing. So that is why the square is taken to negate the effect of any negative terms coming by doing this subtraction. So that is for n k is equal to 1 to n, that is for all the data points and then taking the average of that thing. So that is basically our error function. So by that we can calculate how much error is we are getting. So earlier we have talked about two class of data. Now we are going to extend that to the case of C category. So there are several ways to devise multi-category classifiers using linear discriminant function. So how you can do that? There are two ways of doing that for the multi-classification. One is one against the rest. That is one particular class you are considering and all the others will be not of that. So like just suppose we are considering the W1 case. So W1 that means not of W2. Now if we are considering this particular region, so that will be not of W1. Then other regions will be what? Not of W1. For if you are considering this particular region, that is a W2, other regions will be not of W2. So in this way, suppose it's a 4 class of data are there. So there are 4 class data that is represented by 4 regions. W1, W2, W3 and W4. And when it's W1, so it will be not of W2. Similar way, W2 that means it's not W4. W4 that is it will be not of W3. And W2 that is not of W1. That is, if it belongs to one data belongs to this particular region, so it will not belong to other region. One against the rest. One will be considered, then against others will be decided. So that is one particular hyperplane you can get over here that is going to segregate W1 region with the rest of the region. So you have now decided what is your W1 region and others will be not W1. After that, from this particular region, you have decided what will be your W2. So this will be not of W2. Not of W1 and not of W2. Why not of W1? By this particular hyperplane, you have decided what is W1, what is not W1. Here, you can decide that this is that not of W1. In that not of W1, what is your W2 region? So others will be not of W2 as well. This is basically not of, so this particular region is not of W1, not of W2 and not of W3. And then by this hyperplane, you can decide what will be your W4 region. So that is one question it might arise, that is you have a 4 class of data. Then how many decision boundaries are there? So how many decision boundaries are there? 4. So if there are C categories of data, you need C number of decision boundaries. Now there is a problem. So what happens to this particular region? This is the ambiguous region. For this particular region, if any data belongs to this particular region, you cannot decide their class level. So this is basically the ambiguous region. That is one problem with the one against the rest. Next way of doing this classification for the C categories of data, that is the one against another. So that is W1 and W2. Earlier, what was that? Earlier was if it is W1, then if not, then it will be not of W1. Now it will be, if it is W1, then it can be W2 in that particular fashion. So this is this particular hyperplane that will be between H suffix 1, 2. That is hyperplane that is going to decide between region 1 and region 2. What is region 1? This is the region 1, W1, and this is the region 2, that is the W2. So this hyperplane that is going to segregate these two regions of data. This is between the region 1 and region 3. Region 1 and region 3. Okay. This is between the region 2 and region 4. So that is why the names are there. By that you can decide what will be which hyperplane does what. Now, the another question, same question you can get, how many decision boundaries you need to segregate C categories of data in the concept of one against another. So here the number of decision boundaries are C into C minus 1 divided by 2. If there are 4, so you need 4 into 4 minus 1, that is 3 divided by 2. That is you need basically 6 hyperplanes. Just check, you have 6 hyperplanes over here. This is one particular hyperplane, another hyperplane, another 4 hyperplanes, 5 and 6. So that is, these are the number of decision boundaries you need to segregate 4 class of data points. So more number of decision boundaries are needed if you are doing in the concept of one against another. And earlier the problem was ambiguous region. Here also we have this problem of ambiguous region. So that again stays over here. Now, so as you have a problem, what you need to do? You need to have one solution to the problem. So to avoid the problem with ambiguous regions, what we can do? We can define C linear functions. That is this. For G1x, so that is one value will be up to C, that is 1 to C. Now assign x to Wi if Gix greater than Gjx, where I and J are not equal to, that is J not equal to I. So then assign x to Wi. So that is, you have a data of x, so that is from n number of decision boundaries. For n number of, you have to take the maximum of that, and based on that decision will be taken. So that is our resulting is the linear machine. A linear machine divides the feature space in C convex decision regions. So that is the convex decision regions that you can divide over here. By that, if you are doing the decision boundaries in this particular fashion, then you can just check no ambiguous region are there. Here also for the 3 class of data, no ambiguity in the region decision was there, and for these 5 class of data, then also there is a no ambiguity in designing the decision boundary. The decision boundaries are in such a fashion that there is no ambiguity. If data points can belong to any of the region, and there will be no ambiguity in designing or deciding their class. Now, if x is in region Ri, the Gix is the largest one. So that is, if your Gix is the x will belongs to Ri region. Okay. Now we have to note this particular thing over here. Although there are C into C minus 1 divided by 2 regions, they are typically less decision boundaries. That is 8 instead of 10 in 5 class examples. So here there is a 5 class of data are there. So if you are going by this particular equation, you need 10 decision boundaries. But in this particular example, you have only 8 decision boundaries. So 2 decision boundaries can less number of decision boundaries are needed if you are doing in this particular fashion. Now we are moving to another thing, that is the higher order discriminant function. So if you are moving to the higher order discriminant function, that is more complex decision boundaries are created. So these are the different equations for that. We are not going into the much detail of that. Now what we are going to do, we'll be moving to the SVM. The basics of the linear discriminant function that has already been discussed. Now, by taking that concept, we'll be using that concept and doing the classification using the SVM, that is the support vector machine. So, in that support vector machine, there is a famous problem of tennis example. That is, based on temperature and humidity, you need to decide whether you can play tennis or do not play tennis. If you can play tennis, so that means that is the green dots will be there. And if you cannot play tennis, so that will be blue. So that is, you have a 2 class of data, whether you can play tennis or you cannot play tennis. So by that, it is a problem of two-class classification. Now, so these are the perceptron that we have already just gone through. So recapitulations are not needed. Now we need to decide these two class of data. You need to separate using the linear separator. Now the linear separator can be different linear separators you can draw. This can be one particular linear separator that separates the two data points. This is another linear separator. This is another linear separator. So different linear separators you can draw. But the question arises that which is the optimal one? So you have to choose the optimal linear separator. So how you can choose the optimal linear separator? By this particular concept. So these are the equation, that's the Gx equation divided by mod of W. By that R value can be calculated. So that is one particular example. Now, by deciding for each of the data point, now you have drawn a perpendicular line on the decision boundary. Now you have to identify those data points which are closest to the hyperplane. So those are the closest. Now from this here, by just checking over here, you can easily understand. So these are the data points. Those are closest to the hyperplane. Here the R value and here the R value both are same basically. So these two data points for the blue class of data, blue class. So those are closest to the hyperplane, and here this is the point that is closest to the hyperplane. Now, based on this distance with the hyperplane, this is basically you need to decide the margin rho of the separator is the distance between support. So the data points, those are closest to the hyperplane, those are known as support vectors. So these are going to support this hyperplane. So the data points, so these data point basically is the closest to the hyperplane for this red class. So this is the support vector. So this will be your support vector. And for the blue class, these two data points are closest to the hyperplane. So this is blue are the support vectors for this blue class. And this is your row. So this is your row. So this is the support vector for this particular class, and there are two support vectors for this particular class. Those are represented by these circles, and this is the row, that is the margin. Now, what was the earlier question? Earlier question, you have to choose the optimal linear separator. So now you can easily understand which one will be your optimal one, where the margin will be the highest. So you can draw different straight lines in different directions. But the margin, that is the row you need to calculate, that this distance plus this distance, the summation of these two distance, where this value will be high. So then that will be basically your ideal choice of decision boundary, where you are getting the maximum margin. That's the choice. So why that is your choice? So this is basically the row we have already discussed. So these three are the support vectors, right? In particular equation over here. Now just check if your data points. Suppose you have now some another. You have taken data from another source, and from that data, some data you have fed to the training data set as well. So now your data points can move to different portions. Now you are getting different data points. So suppose now you have data points over here, or you can again have data point over here. Now what happens? So these 2 points are now closest to the decision boundary. So now these 2 points are now becomes the support vectors. Now just check. So as these are the 2 support vectors, if you have the maximum margin, so then if the data points move a little bit, then also you can have proper classification. So now these becomes the support vectors, adding up the new data points. So it is basically new support vectors are decided. Now new new support vectors. So new row value will be, and here the row value will be, that's row bar. Suppose row bar value will be much more lesser than the row. Then also as the data points are in the proper side of the hyperplane. That is, for this hyperplane, the data are in this particular side, in this direction. So that means, so that is the proper classification will be done. Here also the data points are in the right side of the hyperplane. So that is proper classification will be done. So if there are little bit changes in the data point, then also if you have the maximum margin, then proper classification can be obtained. So for that hyperplane for which you can get the maximum margin, that will be our chosen hyperplane. So that is, these are the concept, and how this is coming, as this was the gx if it is greater than this particular scenario, that is earlier discussed. A similar fashion here we are taking, earlier we have taken as greater than 0, less than 0. Here it is whether it is greater than equal to +1 or it is less than equal to -1. So that is, there is a concept of now the margin has been introduced. Based on that, class will be decided. This is very much analogous to the previous lecture, that is on the linear discriminant. That is in the earlier slides we have already discussed. These are the data points, and if this particular equation, that is for the hyperplane equation, if this particular line, for this particular line that is passing the subpolar to the hyperplane, that will be the value will be, that is this region of data, it will be greater than equal to plus, and for this region of data, that is this particular line is equal to -1, and if it is -1, so this particular data, this will be less than equal to -1. So this is the maximum margin classification problem. So that is the maximum margin that you can decide, that is implies that only support vectors are matter, and based on that the maximum margin where you are getting, that will be your chosen hyperplane. Okay, so if you have the data are not linearly separable, so in this particular scenario you can have, this is the data, this belongs over here and red dot belongs over here. So data are not linearly separable. So what you can do, you can introduce a concept of slack variables that you can do. So this is the slack variables by which you can do the soft margin classification. Now we are coming to a very interesting problem, that is, earlier we are talking about the linearly separable data points. Now what happens if the data are not linearly separable? So how it is different over here? In the soft margin classifications, only few data points are not separable. So then if there are very few data points, so among suppose 10 data points, only one is not separable. And for here, suppose 6, 7 data points, one is not separable linearly. So then we are introducing the concept of soft margin classification. But if maximum number of data points are not separable, then we will be moving to the non-linear SVM problem. Okay, so just a second. Am I connected? Hello? Hello, am I audible? Anyone can type in the chat box, or am I audible? Hello?
Yes, ma'am.
Okay, okay. Actually, there was a network issue, so that's why. Okay, I'm sharing the screen once again. Okay, so we are talking about this particular scenario. So if there are very few amount of data points, those are not separable linearly, then we introduce the concept of slack margin. Sorry, slack variables. But if there are all the data points are not linearly separable, so then that slack variables concept is not working. So that is, in this particular scenario, the data sets are linearly separable, right? So you can draw a particular line over here, and by this particular line, the red class and blue class can be easily separable. That is linearly separable. Now, what if this is the concept? That is, the data are in such a fashion that here one particular class of data in the two side of the one particular class. So that is blue class of data is in the middle portion of the red class of data points. That is both side red class of data points are there, and in between you have blue class of data points. So now what you can do? One particular solution is that if the data points are not separable in the current dimensionality, then you can increase the dimensionality. That is, you can map the data to a higher dimensional space. So here we have plotted the data points in a 1D dimension. Now we are moving to the higher dimensional space and we'll be plotting the data in such a fashion the data will represent a parabolic structure. Then that is moving to a higher dimension, you can separate the data points by linear hyperplanes. So just check over here, data points have been plotted in a parabolic format, and you can draw now a hyperplane by which these two are the support vectors, and for the blue class this is the support vector, and by drawing this particular hyperplane you can linearly separable the data points. So that is, if the data points are not separable in the current dimension, you can increase the dimension in such a fashion that the data points becomes linearly separable. So this is the particular function. If this is the concept of the data points in the current dimension, you can increase the data dimensionality in such a fashion that is, it's a two-dimensional data. You have increased it in a three-dimensional space in such a fashion that now the data points becomes linearly separable. So this is all about the support vector machine basic concept. So I can check there are few questions in the chat box. So after that we'll be moving to the next part, that is the application of this SVM in the sign language recognition. So if you have any doubt, you can just raise your hand, then you can unmute yourself, or you can type it in the chat box. So this is basically the theoretical concept of the SVM that is covered. So if anyone has any doubt, you can raise your hand. Just 1 minute of time you can have. Any doubt with anyone, so you can raise your hand, we can unmute yourself and you can ask your question, or you can type it in the chat box. And next we will be moving to the application of SVM for the sign language recognition problem. Any doubt with anyone? Okay.
Yes, students, participants,
Okay.
you can ask your question.
Okay, so we have got one particular problem. That is the what is slack variable. So that's basically a mathematical foundation is there. Slack variables are introduced for those data points which are belongs to the other basically class of data points. So, but there are two concepts of doing the non-linear data points separate by the SVM. So, if there are very few amount of data points that belongs to the other side of the class, the other side of the hyperplane. So for those less number of data points that are basically in the region of the another class, then we introduce the concept of slack variable. So if that one particular book has been suggested, you can check that particular book where the mathematical derivation has been there, how to calculate the slack variables. As the time is very short, so it's not possible to go into the details of that. You can check that there, even the slack variable concept you can understand. And if the data that, and if the all the data points are in the non-linear, then you need to transfer the data point in such a fashion such that the data basically transfers into another dimension in such a way that the data points belongs non-linear data points now belongs in the linear data points. That is, The dimensionality has changed in such a fashion that non-linear data points now becomes linearly separable. That you can do if there are most of the data points are non-linear fashion. Okay, another question we have, that is Manhattan distance related to SVM. Yeah, there are different ways of doing it. That we are doing the simplified one, that is the Euclidean one. We have taken into concept. Different researchers have done different modifications in the SVM, different way. So this is the preliminary concept of SVM we are talking about currently. So that we have done in the Euclidean distance method. Is there is any doubt or anything, or we can move to the application of SVM? Okay, so I think there is no doubt with anyone. So we are moving to the application. Okay, so here, so that is the particular. Okay, just sorry. So here, this particular application that we will be talking about for this particular conference paper. So this conference paper is published by the Springer Fourth International Conference on Advanced Computing, Networking and Informatics. That is the short form was ICS-CNI 2016. And this particular conference were organized in the NIT Rourkela, where this paper was there. This is available in the internet. You can just take the screenshot. We are just checking in the internet in the Google Scholar. You can find the paper from there in the internet. So this is the paper. So in this paper, we have used AVL3 as well as SVM to recognize the recognize the gestures that basically forms the sign language. So here we are talking about the gesture recognition in the domain of sign language application. So in the last class, we have already discussed what is the gesture. So body gesture is something by which non-verbal communication between two persons can be done. In this particular application, we'll be talking about gesture recognition using the Microsoft Kinect sensor. So what is Microsoft Kinect sensor? By using Microsoft Kinect sensor, human body can be represented by the 20 body joint coordinates. And for each of the body joint coordinate, you can have 3 dimensions of data. That is in the X, Y, and Z dimensions of the data. So first we'll be having the one particular video. This particular video was shoot during my PhD days in the Artificial Intelligence Lab in the Jadavpur University under the guidance of Professor Amit Ponar. This particular lab, you can just understand what is the how the Kinect actually works and the actual implementation of the Kinect sensor that you can understand over here. So I'll be switching off the video. The voice of the video you can listen, right? Uh, Voice from the video is coming. You
No,
can just
ma'am. For
type in.
that, you have to just reshare with the option that share the sound.
Okay, so I have to share this VLC player only.
No, ma'am. You have to just screen share with there is a option at the bottom share sound.
Okay. Just a second.
Yes, ma'am.
Share sound. Okay. Yes. Oh, just let me know whether you can listen to the voice.
Hello everyone, I am
Yes,
Sripaula
ma'am. It is
Sharma
audible.
and today I am going to demonstrate the working principle of Microsoft Kinect sensor. This device has an IR emitter, IR detector, a 8-bit VGA resolution RGB camera, and also it has an multi-array microphone. The name Kinect has been derived from the word kinematics, as it can sense the human being in dynamic condition. Now, I would like you to meet our two subjects, Vishwarup and Tanuka. Now, in the computer screen, you can see three outputs obtained from the kinet sensor. Left, the depth of the subject is acquired by the IR sensor. In the extreme right, the RGB video of 8-bit VGA resolution is acquired by the RGB camera. And in the middle, the skeleton of the subject based on RGB and IR data is obtained. Those skeletons are formed using 20 Cartesian joint coordinates in 3-dimensional space. Now, I would like to demonstrate how the kinet sensor can be used for healthcare applications. Suppose a subject is trying to fetch then sudden can occur nerve root in the lower back. This gesture is known as prolapse intervertebral disc. Another common symptom can be observed in young individuals who tend to work in sitting posture for 7 to 8 hours for office work. This gesture is known as trapezius fibromyalgia. Again, due to injury, there can be pain in the knee. This gesture is known as knee sprain.
So we have just checked that is what is the kinet sensor and how it actually looks. So that is already been shown to you. So we are not going to cover those things that will be in the slides. So we are moving to how the work has been done. So in this particular scenario, there can be some static joints and some dynamic joints. So the kinet sensor represents the human body into 20 body joint coordinates. When the person is performing the sign languages, some joints can move. So those joints will be dynamic joints. Some joints cannot move. So those will be the static joints. And as the human body will be represented by the 20 body joint coordinates, so the summation of the static and the dynamic joint will be 20. Now for each of the joints, there is a weight adaptation. So for if it is the S for the static, that is this particular scenario. So how many values will be there? As all the joint data points will be in the 3-dimensional. So there will be X, Y, and Z dimension. So for each of the static as well as for the dynamic joint, you are going to have its corresponding X, Y, and Z coordinate values. So this is the weight values. Each of the joint along one particular dimension is now associated with a weight. And summations of all the weights is taken as the nearly equal to 1. This is how weight adaptation is done. After the weight adaptation for static and dynamic body joints, we are moving to the feature extraction using in order expression. So for any type of a tree, there are three ways of doing the expression. You can represent it in pre-order, in order, pre-order, post-order. I hope you already know that is where the parent node belongs. Based on that, in, pre, and pro are there. That is in the pre head, that is the uh, parent node will be in the previous stage. In means it will be between the left and right children. That is the in order expressions for the AVL tree that has been generated. And that in order expression is the feature extraction. And here the T, that is the number of frames to obtain to express a particular gesture G. So it's a dynamic gestures has been taken into consider, and based on that, for one particular frame, suppose it's the ith frame. So the expression of the in order will be IOI. IO, that is in order. In order we are talking, and suffix will be I. as there are t number of frames can be there. So that is multi-value will be 1 to capital. Then there will be this many number of in-order expression. And this total scenario will be your feature. So this is one particular RGB image of the subject. This is the kinase sensor, and by the kinase sensor, this particular corresponding skeleton is obtained. After that, this is the AVL tree that has been generated, and for this AVL tree, the in-order expression is calculated, and it is repeated for t number of frames, that is all the frames, and after that, features is classified using the SVM. So for this particular scenario, we have taken into account 12 gestures related to sign language application. That is the move down to up, move up to down, move left to right, move right to left, then pushing, grabbing. These are the 12 basically body gestures from here to here that has been considered for this experiment. And each gesture is taken for the period of 3 seconds of duration. That is, kinase sensor frame rate is 30 frames per second. So now how many frames you have? You have 90 frames. So that is 3 seconds of data. For each second you have 30 frames. So that is total number of frames. Now we have 90 frames. And we have 3 different data sets based on the different age groups of the subject. So the total data points is now divided. The total data set has been taken in the concept of different age groups. Based on different age group, 3 different data sets. And we have empirically, that is basically manually, we have basically calculated the values of static and dynamic by actually basically checking how the gestures are performing. You can just check the gestures are basically the movement of the hand. So that is a core body and the legs that basically belongs to the static joints, and the dynamic joints are the basically hand joints. These are the weights that are being considered, and these are the weights for the dynamics. And the in-order expression is generated for the AVL tree. That is, this is the one particular in-order expression, and the unknown gesture, that is this unknown gesture, now currently recognized as the applause. That is this one. So that is the correct recognition can be done by this particular scenario. Now, as already in the last lecture we have discussed, our experiment can give us very good result. But whenever we are publishing any paper, we have to compare it with other existing algorithms. For the particular scenario, we have compared with other existing algorithms like KNN, k-nearest neighbor, ensemble list tree, that is EDT, and backpropagation neural network. And here you can check the backpropagation neural network have equal and sometimes better result for this particular 4 performance matrices, that is precision, recall, accuracy, and error. So you can tell me that is, ma'am, backpropagation neural network, that is BPNN, is having better accuracy or nearly equal accuracy with SVM. Then why not BPNN, our correct choice? The answer lies over here. As for the BPNN, time complexity is much higher than the SVM. So whenever we are designing one particular algorithm, we need to, only accuracy is not our ultimate criteria. We need to take into consideration how much time we needed to classify the data. That is, we need to take the concept of the timing complexity. Based on the timing complexity, now you can check BPNN is very worse. That is, higher timing complexity means higher time it takes. So BPNN performance is worse than the SVM. So our chosen classifier is the SVM, that is the support vector. Now, after that also, we have done a statistical analysis, that is a Friedman test. That is our last class. It has been decided. By that, the null hypothesis has been rejected, as this was the chi-square F values has taken 8.2, that is greater than our threshold value. So that is a null hypothesis is rejected. So null hypothesis rejected, that means SVM is the best choice. That is done. So these are the conclusion. That is, we have get the higher accuracy rate of 88.3% that we have taken. And here basically we are considering the hand motions that are basically, each hand motion is depicting one particular sign language by which people used to, that is a non-verbal communication between different persons can be done. That is, and here the feature extraction has been done using the in-order expression, and the classifier is chosen as the SPF. This is the accuracy rate we have obtained over here. And one of the pitfall is that it's basically taken the consideration of the upward body movement. So that is, upward body movement is one particular drawback of this particular word. You can include much more complex body gestures where not only the upper body of the human or the lower body will be also going to move. Then, if the total human body is moving, and then how much accuracy you can get, that can be one particular future word that you can do after taking the inspiration from this paper. So, this is all about today's lecture. Now we will discuss different questions you have. So, looking for your questions. So, if you have any doubt, you can ask me or you can raise your hand. We can, yeah. If you have any doubt, you can type it in the chat box or you can raise your hands. We can unmute you. Now the session is open for all. You can ask your queries. The best way, you can raise your hand, then you do not need to type the queries in the chat box.
Dear students and participants, please raise your hand if you have any question. Dear students, if you have any questions, please raise your hand.